Hey, welcome back. I'm sorry for the long wait between videos. I've had a lot of work going on with my PhD over the past few months. However, today I want to talk about cross-validation. Why should machine learning projects use cross-validation, what it is, and how is it done? First, to know why cross-validation is so important, we need to do just a tiny bit of statistics. Don't go away though, it's not anything too deep. First, we need to look at flipping a coin. Would you be able to determine if a coin is fair just by flipping it one time? If you would have a 50-50 shot of guessing correctly. However, the more you flip the coin, the higher and higher your confidence gets that you can say whether the coin is fair or not. The same thing can be said about machine learning models. If you train and validate a model one time, then that is similar to flipping only a coin one time and saying whether the coin is fair. In this case, is saying that the model performance is whatever accuracy is output from your validation. So how can we stretch this analogy to say that we trained our model multiple times, thus having higher confidence in its performance? That is where cross-validation comes in. So we know we want to train the model more than once. How many times should we train this model, and how should that data be split up? Let's say that every time we train the model, we call that training session a fold. So if we train the model 5 times, we would then say that we performed a 5-fold cross-validation. Now for each fold, how do we select? What is the training data and what is the validation data? Usually when you want to do a train test split on your dataset, you would usually have a 70% training, 20% validation, and 10% test split up. To set up an example here, we're just going to have a 90% training dataset and a 10% test. That 10% test dataset would be set off to the side and not used at all during cross-validation. Now let's build a figure where on the left-hand side we have each fold going from the top right to being fold number 1 and the bottom left being fold number 5. Then the top of our figure from left to right, we have all of our data points such that looking over the entire top portion of our graph will give us the entire 90% training dataset. Now the word cross-validation has the word validation in it, so of course we need to have a validation dataset formed out of this 90% training dataset. What we will do is we will divide the training dataset into 5 different sets. The 5 here is coming from the number of folds that we are performing. If we wanted to do a 10-fold cross-validation, then we would have our training dataset split up into 10 sections. Now we can go over our figure and label each fold having a single validation set out of all of those smaller sets we made. The key here is that each fold has a different validation set. So we can go over each fold and mark off the validation set one at a time as we go down so that it forms a diagonal in the figure. The training will be done on the rest of that data set for each fold. So all of those other sections that are not marked as the validation data set are then clumped back together and trained on. The issue is that while you do want to have a lot of folds, you end up shrinking your training data set so much that you actually cannot properly train your model. Because of this, the standard is usually 5-fold cross-validation when cross-validation is performed. However, that can vary by field. For example, in biology, it is not uncommon to see 10-fold cross-validation used. It all depends in the end on the data that you're using and how much you actually have of that data. Final note is that every fold is a different model that is being trained. So again, for 5-fold cross-validation, you are actually going to be training 5 different models, each on a different training dataset and a different validation dataset. One thing to note, though, is that we do not use these models in production. Once you are satisfied with your cross-validation performance, possibly after some tuning of your model and whatnot, you then take your whole 90% training data set and your test and you train your final model. You can then test the model on that test data set that you set aside earlier to come up with your final accuracy or whatever performance metric you might be using. Once we have all of the training and validation sets set up, we can then go to train and test our model on those data sets. Then comes the time of measuring the performance of those models. There are two ways that you can split up the performance metric. Of course, you can use whichever performance metric you like accuracy, F1, or ROC. If you are curious about F1 score, accuracy, or ROC, and when you should and should not use them, then I'll encourage you to go check out the other video I made on these performance metrics. A link to that will be up above at the top of the video, as well as in the description below. However, there are two ways that you can average performance over all models. For each of those models, there is a micro and macro averaging. The difference between micro and macro averaging is whether or not you want to calculate the performance metrics during cross-validation or after cross-validation. With micro averaging, you take all of your positive and negative samples along with your positive and negative predictions, and you are tracking them across all of your models as they are predicting. However, with macro averaging, you are calculating the performance metric after every model is finished training and validating. Then you are averaging over all of those performance metrics once cross-validation is over. On deciding which one to choose, it somewhat depends on you, and it somewhat depends on your dataset, such as is your dataset skewed at all? Are you working with binary versus multi-class labels? You could also use both and make sure that they come within a margin of error of each other as well. Because my datasets that I usually use are very skewed, I tend to work with macro averaging. However, I have also used micro averaging before when I have datasets that are not as skewed. Let's give an example to wrap up everything that we've been talking about. Let's say that we had a training dataset of, say, 11 samples. We want to do two-fold cross-validation, and we want to use accuracy as a performance metric. We're not sure though whether we want to use micro or macro averaging, so we'll use both and see what comes out. Since we are doing two-fold cross-validation, that means that one validation fold is 5 samples and the other validation fold is 6 samples. Now let's say that the validation fold with 5 samples got 1 correct and the validation fold with 6 samples got 3 correct. Calculating accuracy for these two models then shows that the one model got 20% accuracy while the other got 50% accuracy. If we add both of those accuracies up and divide by 2, we are left with the macro average accuracy of 35%. To get the micro average, we take the 1 correct prediction from the one validation fold and the 3 correct predictions from the other validation fold and add those together to get 4. Then we add the total number of samples, in this case that was 5 plus 6 to get 11. Finally, we divide 4 by 11 to get 36% or 0.3636 repeating. So we can see there was a small difference between micro and macro averaging in this example. However, they're not that far off, with one being 36% and 35%. So we could most likely give an estimate of a 35% accuracy is to be expected out of a final model if we would then train a final model using this data. Now let's take everything we learned and wrap it all up. Now you should know that the reason that we chose cross-validation is because we want to have confidence in the accuracies or performance metrics that we are giving. You also know how cross-validation is done by splitting the datasets up and training multiple models. And you also know that the two different types of averaging that you can do after cross-validation is performed is either micro or macro averaging. Hopefully you were able to learn something out of this video, or possibly even get a little more clarification on cross-validation or why it's even important. If you did, then please like the video and possibly subscribe, as I would like to make more of these educational machine learning videos and possibly even projects in the future. Thank you all, and I will see you in the next video.